Here is section 10.4, conditional and absolute convergence. This is another topic that's not directly covered on the BC exam, as far as I can tell, but there are some pieces in it that you should still know about, and the alternating series piece is what you need to know. Actually, conditional and absolute only works for alternating, so I don't know if you need it or not. So we'll teach it to you. I'll get back to you if you need to know more information. Let's look at our notes. I'm still here. 10.4, we're still in that yellow packet. Conditional and absolute convergence. A series is absolutely convergent if the absolute value of that series also converges. What are they talking about? Well, this piece, and I feel like our notes are a little backwards here. Positive, negative, positive, negative. This is alternating. This is the piece that you really need. The Leibniz test for alternating series. Let A sub n be a decreasing positive sequence. So if it's decreasing positive and converges to 0, those are the three criteria that you need. Decreasing positive and tends towards 0. Then the following alternating series converges. So positive, negative, positive, negative, positive, negative. It could start negative and then go positive. It doesn't really matter, just as long as those signs flip-flop. If those things are true, and then those signs change, you can say that it converges. Yeah, that's a mouthful. So if you have these terms that are positive, decreasing, and converge to 0, and then if you start to change the signs, this is called an alternating series. That alternating series will also converge. I think this is a little bit more clear. Maybe, maybe not. This -1 to the n, that's the piece that makes it alternating. I know I've mentioned that in class before. It converges if a sub k is greater than a sub k plus 1. So if the term that you're at is larger than the term that you're going to, and the limit goes to 0, it converges if those other criteria are met. Then inside of that, you can tell me if it's conditional convergence or absolute convergence. Yeah, so alternating series. So let's go back. This is an alternating series, positive, negative, positive, negative. It converges absolutely because if we take just the positive values of that and fill it into the series 1 over n squared, this converges by the p-test. So because the absolute version of it converges, the positive version converges, the alternating piece converges, then we can say it's absolutely convergent. I know, it's a mouthful, total mouthful. So here's the steps to make that happen that I just talked about out loud. So let's write it down. If we look at the formula for this is the first term, the second term, the third term, the fourth term. This is going to be something over n squared. And it changes signs. There's definitely a 1 there. But positive, negative, positive, negative. Well, the first term is positive, so it's not -1 to the n. It's -1 to the n plus 1 or minus 1. I'm going to scooch this one over a little bit. This piece right here makes it alternating. I'm going to write this out a little bit differently. -1 to the n plus 1 over n squared. That's easier to see. So this is the alternating piece, and this is the actual series. So if you look at this piece, that's the whole thing. If you look at 1 over n squared, well, those are positive terms. They decrease, and they tend towards 0. So because this piece is alternating, I can say that this series converges by the alternating series test. How else do I want to say that? That's Jacob in the background you hear. So this converges by alternating series test. which is on the next page. Now, if I look at just the positive piece, n equals 0 to infinity of 1 over n squared, this one converges by the p-test. So this is the positive only version. So because the positive only version, the absolute value, converges, and the alternating piece converges, you can actually say that this is absolutely convergent. Now, again, I don't know if this is going to be included on that BC exam with the alternating series test. We'll have to see. Pardon me. Example 2. Does this sum of this series, 2 to infinity of negative 1 to the n over n to the ln of n, converge? Absolutely. Well, look at the alternating piece. Let's see if that converges at first. Well, this is negative 1 to the n is alternating. If I've got 1 over n, natural log of n, this piece is positive, decreasing, and tend towards 0. So this would converge by the alternating series test. We just have to decide, okay, is it absolutely convergent or conditionally convergent? So this one converges. Converges by alternating series test. Now, we need to see if this piece converges, just the positive piece. So we're going to rewrite this, n equals 2 to infinity. Don't need the negative 1 to the n, that's the alternating piece of it. 1 over x, natural log of x. Well, I should keep those notes. Then you want to hit this list. Well, which rule can I use to figure out if it converges or not? Is it geometric? Nope. P-series? Not that lucky. Integral test. Well, this is a natural log of n. What's the derivative of natural log? 1 over. So 1 over x would be the derivative of natural log of x. Let's try that. Actually, no, that's what it is. So that's just what we'll do. So we are going to use integral test. We are going to write this as 2 to infinity, 1 over x, natural log of x dx. We need u substitution, where u is the natural log of x, and du is the derivative of that, 1 over x dx. Now, because this is an improper integral, we're going to use limit again. As r approaches infinity. How do we write this? 2 to the r, 1 over x, well, 1 over x natural log of x dx. So that makes it the limit piece. If I convert this to u substitution, the limit as r approaches infinity, 2 to the r, 1 over u. In terms of that u, we need the 1 over x dx, which we have, 1 over x dx, so there's the du piece. The natural log of x becomes the u, so 1 over u du. Now, just like the other problem, I goofed on my boundaries. I should change these. This would be the natural log of 2, and this would be the natural log of r. Now, if I integrate 1 over u, that's really the natural log of u. So this is the limit as r approaches infinity, natural log absolute value of u, that's the antiderivative of 1 over u, from the natural log of 2 to the natural log of r. And now we substitute these in. The limit as r approaches infinity, the natural log of r minus the natural log, I know this looks ridiculous, and the natural log of 2. Here's the thing, this is a number, I don't care what it is, it's a number. This is infinity. The natural log of infinity is infinity, and then the natural log of infinity again is still infinity. This is infinity, but we don't say infinity anymore, we say diverges. We say that this diverges. So, because this diverges, Nope, not this diverges. This converges. See, I'm so out of this. This converges by the alternating series test, but the positive piece of it diverges. So you say that this is my original, -1 to the n, 1 over n natural log of n, is conditionally convergent. So the original converges by the alternating series test, positive, negative, positive, negative, positive, negative, gets closer and closer and closer to 0. But because the positive only version of that diverges, we say that it's conditionally convergent. There's my conditionally convergent. An infinite series is conditionally convergent if it converges, but the absolute value of it diverges. And so that's what's going on right here. And here's the alternating series test we already talked about. If you have these terms, and if you just look at the positive values of them, they get smaller and smaller and smaller. It's an alternating series and it converges. That's one of the best tests. Second best probably to the p-series. P-series is best. Alternating series might be the second best. So we want to show that this is conditionally convergent and that the sum is between 0 and 1. Well, let's start with the conditionally convergent piece. Let me flip my own notes here. So if I look at 1 over the square root of n, these terms are positive, they are decreasing, and they get closer and closer and closer to 0. The higher the n you put in there, all that's true. So the original converges by alternating series. Now we want to look at just this piece to figure out if the positive, if that converges, then we say absolutely convergent. If this diverges, then we say conditionally convergent for the original. So let's look at this one. We're only looking at the positive terms now, 1 over the square root of n. Now, how can I rewrite that so it meets one of these lovely tests? I see a square root there. I can write that as an exponent. So this is n equals 1 to infinity, 1 over n to the 1/2. Hey, guess what? What's that exponent? It's 1/2. That's less than 1. This is a p-series. This diverges. So because the positive version of it diverges, we can say that the original does converge by the alternating series test, but it's conditionally convergent. Now, what about this other piece here? That the sum is between 0 and 1. I'm not interested in that today. Let's just skip over that. Okay? Okay. Works for me. It was almost the same thing. So we want to show that this one is conditionally convergent. So that -1 to the n, or that -1 to the n plus 1 or n minus 1, that's your red flag that this is alternating series. So alternating series. Then you have to look at the piece that's not alternating, which is 1 over n. So 1 over n, positive, positive, decreasing tends towards 0. So that means we can use the alternating series test. If I look at this one, this is convergent. I kind of like to write it as this with the alternating piece in the front, but this one converges by alternating series. There's Jacob here in the background. All right, now if I look at just the positive piece, you want to ask yourself, does that piece converge or diverge? Well, this piece diverges. How do I know? There's two choices. Everybody's favorite, p-test. that exponent is less than or equal to 1. This is 1 right here. So this diverges by the p-test. But every year I have a few students that just love the integral test. Anytime they see it, they use it where they can. If you went through the steps of the integral test, you would see that this also diverges. And we did that on the last notes. So because the positive version diverges, and the alternating piece converges, we say that this is conditionally convergent. I should say that original piece is. Now, that's all I have for an alternating series test, I think. Let me double check. That is all I have for your assessment. Yeah. That is everything I have for alternating series test. I don't know, again, how much that conditional absolute convergence thing we're going to need for the AP exam. More details will be coming. But I do have to say the videos that the folks at the AP classroom are putting out, or College Board are putting out, are really, really good. I sat down and watched some of them. I know you're going to have your schedules full of Zoom meetings and office hours and work that you have to do. But if you can catch some of those sometime, they're really, really good. The AB ones, if you're going to take the AB exam or if you're going to take the BC exam for sure, are really, really helpful. That's the woman who made the circuits that you love so much. I'll have to find some of those to do while we're home. And then the BC exam one, I saw some of those as well. Again, they're really, really good. Those are the 4 people that kind of moderate some of those message boards that I've been on, where they release some really good resources. So I highly, highly, highly recommend the videos. You try to keep them to about 45 minutes. They start out with a warm-up. There's materials that you can download and work along with them as they go. And then they have a little closure activity at the end. They're good. It's just like sitting in the classroom and kind of goofy with one another. So I hope that you will check those out. The assignment that goes along with this is assignment number 4. I'll probably look through those problems and alter the assignment a little bit, but look for updates in that Google Classroom.